أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. We'll start this short video to show you how to solve the last quiz number 2, which was basically the parallel plate capacitor, finding the electric field in a parallel in the three regions between the parallel plates, in this region, in this region, and in this region. And the question is asking you to use Gauss's law. And so if you remember, Gauss's law is equal or is defined as the electric field dotted with the area over a closed surface is equal to Q enclosed over epsilon. That's what the electric field is defined as. Okay, so let's see how we're going to use that, or how we're going to find the electric field in these three regions. And the way we're going to do that by first, as suggested in the quiz. So this is the quiz, just so that you remind you what the quiz is. This is the problem that you were asked to solve, and we wanted to solve the electric field, or use Gauss's law to find the electric field for the negative plate and for the positive plate, and then we put these the two plates together and see what we get. Okay, so let's start. So let's start with the positive plate, because we've done this many times, and I think everybody is familiar with that. So if we have the positive plate like this, to get to calculate the electric field using Gauss's law, I need to build a Gaussian surface, and this Gaussian surface is a cylinder, as we've discussed in class, and we're going to split or divide the cylinder into three areas. This is surface 1, or three surfaces. This is surface 1, surface 2, and the curved part is surface 3. And we know that for a positive charge, the electric field is away from the charge. We've seen that again, so this is our electric field. The other thing that we need to know is the direction of the area, which is the normal vector. So this is N1, this is N1, N2, and this is N3 hat. Okay, so we should notice that the angle between the electric field and N1 hat is 0. Okay, so theta is equal to 0. In this case, again, the angle between the electric field and N hat, theta, is also equal to 0. And the angle between the electric field and N3 hat, theta, is equal to 90. Okay, so this is the electric field, is this direction. So these are the three surfaces. So we have to break our Gauss's law. We have to break it, as I said, into three surfaces. And let's say in the following way. So surface 1, so surface 1 EDA plus surface 2 EDA 2. Okay, this is DA1 plus surface 3 EDA 3. And all of this is equal to Q enclosed over epsilon naught. Okay, so now since we know from the angles that we just had that this is 0, this is 0, and this is 90, we know that cosine 90 will be 0, so which means that surface 3 will actually give me a 0 contribution to the electric field. And the electric field on both sides will be the same. So these two are exactly the same, the angle is the same, everything the same. So for S1 and S2, I'm just going to say EDA is equal to, rather than A1 and A2 because they're the same, is Q enclosed over epsilon naught. And as you said, the angle here in both cases is 0. So EDA cosine theta is equal to 1. So that means I have 2, and the electric field is uniform, so that goes out the field, and dA is A. So I get 2EA equals to Q enclosed over epsilon naught. Okay. Now epsilon naught for the positive one epsilon naught is nothing more than sigma multiplied by A. The enclosed charge is nothing more than sigma multiplied by A. So if I do that, then I get the electric field sigma A over 2 epsilon naught A. The A's will go with the A, and then I have the electric field E for the positive plate is equal to sigma over 2 epsilon naught. That's in the region here near the plate, and in the region here near the plate. That's what the electric field is. And if you're here, the direction of the electric field is I hat, and if you're here, the direction of the minus I hat. It depends on which region are you working on. Okay. So now let's move to the negative plate, because the negative plate is the one that is a little bit not challenging, but it's a little bit different. Okay, so the negative plate, I have a negative plate. It has a sigma, a negative sigma charge per unit area. That means the electric field is directed this way. The electric field is directed this way. Remember, for the positive plate, it was directed that way. So when I have my Gaussian, again, I'm going to get this, an S1, or I'm going to divide them into S1, S2, and S3. But notice that, and this is where the difference is, notice that the unit area, in this case, N1 hat, is this way, and N2 hat is this way, while N3 hat is still the same where it is. Okay? So that means the angle between these guys is 180. So theta 1 and theta 2 is 180 degrees, not 0. That means cosine 180 is equal to minus 1. So if I do the same thing, if I go and do break my Gauss's law into 3 surfaces, so surface 1 E dA 1 plus surface 2 E dA 2 plus, of course, surface 3 E dA 3. Now we know that dA3, the angle between E and N hat 3 is 90, so this will again, cosine 90 will be 0, and this will go to 0. And then I have only 2 of these guys. Okay, so let's do them again. So remember, the angle between them is 180, so that means I have again E2 E dA, right, is equal to Q enclosed over epsilon naught. EDA is EDA cosine 180, so that means minus 2 E, and I have an A is equal to Q enclosed over epsilon naught. Well, what is the enclosed Q when you have a negative charge like this? What's the enclosed Q? The enclosed Q is now minus, because this is minus sigma A. So if I put that in here, then I get EA is minus 2 EA is equal to minus sigma A divided by epsilon, and the A will go with the A, and the minus will go with the minus, and again I have an E, the electric field is equal to sigma over 2 epsilon. Okay, that's what the electric field equals to. Okay, so what does this mean? Let's just put things together. So this is the electric field due to the negative plate. So that means if I put these guys together, okay, this is my positive plate. Okay, it's my positive plate. Okay, and this is my negative plate. I'm just going to give more room here. Negative plate. Okay, the electric field for the negative plate is into, right? It's into the sheet, right? And for the positive plate, it's out or away from the sheet. Okay, so at any point, what is this guy equal to? This is equal to sigma over 2 epsilon, and this guy is equal to sigma over 2 epsilon. Okay? So when I add these two guys together, so that the net field inside is equal to the sum of these two guys, which is sigma over epsilon, not as we had seen before. Now, how about the electric field here? Well, the electric field here, again, this guy here is for the positive electric field is this way, and I had it's equal to sigma over epsilon, sigma over epsilon, that's right, sigma over epsilon. And the electric field due to this guy, due to the negative one, so this is E, and E negative is equal to sigma over epsilon. And remember, one of them is I hat, and one of them is negative I hat, so when you add E total in this region, it will give you 0. Okay. Similarly here, E total is equal to 0, and that's so because the electric field here is this way, the E negative, and the positive one will be E positive this way, and when you add them up as vectors, you get 0, and that's it. So the electric field here is added. You add the vectors because of the same direction. The electric field here subtracts because they're opposite directions, and the same thing here. The electric field as because they're in the opposite direction. That's it. So this is the solution to the parallel plate capacitor problem, finding the electric field using Gauss's law. And I'll see you in the next video. Thank you.